application of principal G bundles on a 4-manifold.
So the first stumbling block in this theory is to get the spelling of principal correct. When I see that.
No, you don't know how I've spelled it.
No, I don't.
And I think I spelled it correctly. So, okay. Who's on first? Okay, so G is supposed to be a simple compact Lie group. Right. So the basic facts are that pi1 of G is finite, and in fact, it's a subgroup of the center of the universal cover of G. And pi3 of G is Z, and there is a map from SU2, which is famously the 3-sphere, to G, which gives the generator. And when I say the generator, what do I mean? Well, I can think of this guy as giving me then a clutching function for a bundle on the 4-sphere. So this implies a bundle, which I will call Pj for a second, over S4, where you glue using this composite map, a G bundle, and the key thing that the key characteristic class that we're looking at is P1 of the adjoint bundle. And we are going to fix this generator so that this is some constant that depends on the group and is negative, because with if you have an anti-self dual connection, its Pontryagin number is negative from the energy formula. It's Chern class. If it was an SUN bundle, the Chern class is going to be of the vector bundle is going to be positive, but the Pontryagin class of the adjoint bundle is going to be negative. So that's the convention, and C of SUN is 4n, C of SO3 is 4, etc. Or you can look it up in a TH and Singer what the answer is in general. Okay, so principal G bundle is going to have two characteristic classes. There's going to be a characteristic class W of P, which is an H2 of X with coefficients in pi1 of G. And then there's the Pontryagin class of the adjoint bundle. In H4 of X Z. But this might satisfy some divisibility properties, and those divisibility properties might even be they'll be constrained by W. Okay, I'm not going to say exactly what they are, but we'll use the divergence theorem to prove that. No, we won't do that. What else do I want to say about that? Yeah. So, but the P and P prime to X are isomorphic if and only if these two characteristic classes are the same. Right? And if, if G is SON, then W of P is just what is just the second Stiefel-Whitney class, but if G is PUN, then W of P, then what is it? Yeah. So the algebraic geometers would call the complexified version of this story an Azumaya algebra. Yeah. And W of P is called the Brouwer class in that case. So you can impress your algebraic geometry friends that you actually know what that is. But anyway, it's called the Brouwer class. Right, both of these are the obstruction. This is the obstruction to lifting this to a spin end bundle. And then this is the obstruction to lifting it to a UN bundle. Sorry, SUN bundle. Okay. And what else I want to say? Right. Now, there's a natural action of Z on bundles, which is we can, if we have, which I kind of mentioned last time, but I want to say it a little more clearly this time, I can send P to P plus 1. What does that mean? That means I'm going to take here's my 4-manifold X. I take a point and a ball around that point, and I collapse the boundary of the ball to a point. So I get a map to another copy of X and the force sphere, and here I have this bundle Pj. I have my original bundle P, and then I have this map F, and F star of the sort of, so that's the wedge of these guys, F star of the wedge of these guys, that's P plus 1. Now, I could have also taken kind of, let me call this one P plus now. I could also take P minus, where the clutching function is J inverse, and then I can pull back these guys, and I get P plus or minus 1. So in this way, you get, now you can keep doing this, and you can get then, if you pick a P, then P plus Z runs through all isomorphism classes of bundles, G bundles, on X with what property? Peter. You weren't paying attention, were you?
Not on physics.
Yes.
A fixed P1 class? Or
No.
fixed W?
Fixed W class. So with W of P equals some, WP prime equal to some fixed W. So this I mean, it's important to, this shifts P1 by C of G. So I should have said that. So P1 of P. All I brought the colors. P1 of P plus 1 is sadly not P1 plus 1, because that would be completely incomprehensible. It's P1 plus C of G. Okay? Anyway, now, yeah, sorry.
Is it possible to get every P1? Every possible value of P1 and W, or?
Yeah, so again, there is secretly a constraint between W and P1. So in this case, or well, if G is SO3, then P1 of P is congruent to the Pointryagin square of W2 of P mod 4. So, so if you have a class in H2 with Z2 coefficients of a 4 manifold, it actually has a well-defined square mod 4, and P1 has to be equal to that. Okay, and then there's a more general story for other bundles, but the full, at least in this case, the full classification theorem says that all bundles with this this can be anything, and as long as you have this condition, then you get a P. Okay. So there's.
Of course, I thought
Yeah?
I thought that G is always SO3 and C of G is always 4. But does C of G have some kind of description, like representation?
Yeah. I mean, C of G is, well, I mean, that's sort of its description. I mean, that is its description,
Okay.
which you can, which is some story about sum over roots. I mean, it's the, it's. I forget if it's exactly the Coxeter number of the group, or that's like, it's the Coxeter number twice the Coxeter number or something like that. Anyway, so okay, so there's that, and then well, now I can state Uhlenbeck's compactification a little bit more clearly, and I'll introduce a bit more notation. So on the one hand, if I look at this NP of x g, and I take a sequence in here, X is closed oriented compact 4 manifold. Right? That's the set of A such that F S A equals 0, mod gauge group of P. Then there exists a subsequence which I will still call AI, a collection of points let's call that collection S inside X, finite collection, a P prime, which is equal to P minus L. L is greater than or equal to K. A infinity, a gauge equivalence class of connection in the moduli space of P prime, such that these AIs restricted to X minus X converge to A on X minus S, in C infinity on compact subsets. And so again, you're supposed to think that some energy's bubbling off at these points. Also, if I look at the curvature form, curvature 4 form, this converge of the sequence AI, so that remember that this guy is the wedge and minus killing form. This thing's supposed to be positive definite. This thing converges weakly to the limiting guy plus a sum 2 pi squared ni, 2 pi squared c of g, some ni delta function at xi, I equals 1 to k. And now I can tell you more accurately what L is. L is the sum of the ni. Okay? So you're supposed to think again that some energy is bubbling off. The energy is that bubbles off at a point is constrained to be the energy of, C is negative. So, and this is positive. So the energy is constrained to be an integral multiple of the minimal energy of an instanton on the force sphere for that group. Okay? And then we can introduce the space of ideal instantons. That's equal to the disjoint union. L greater than or equal to 0 of MP minus L of X times the L symmetric product of X. So as L gets bigger, the energy here gets smaller. So eventually the energy is negative. Eventually this is negative. Eventually it's negative. This becomes empty if L is sufficiently large. So this is a finite union, and we topologize it topology. You have to really say this a little bit better, but generated by these 3 things, by 1 and 2. Okay, and then the Uhlenbeck compactification and check. That's the closure. In the space of ideal instantons. Okay? Now, what do we want to? No. Yeah. So remember we we have this space which doesn't depend on the metric quotient of all connections by gauge transformations that contains the irreducible connections and there's oh yeah, I forgot to say we had a formal dimension of this NP of xg, which is equal to minus 2p1 of add p minus the dimension of g over 2 Euler characteristic of x plus signature of x. And this is also 1 minus b1 of x plus b plus of x. Right. So we'd like to know two very basic questions. So when is the intersection of the part of the moduli space that consists of irreducible things, when is this thing smooth of dimension equal to this formal dimension, that what the index would predicts the dimension should be, and B, when is the moduli space contained in the in the irreducible connections. So yeah.
Why is the Uhlenbeck activation not just for
I mean, so there's no reason for it to be, and it's not always. I mean, for example, if so, the silliest example of an instanton is a flat connection. If B plus is positive, though there will be flat connections. I mean, that's already starting to address B here. So let me answer B, and then I'll go back to your questions. And note, if WP equals 0, then P can be trivial. And then has the trivial connection. And then if B plus is positive, and let's say B1 is still 0, then the formal dimension of the moduli space is minus, this is trivial, so that means that P1 is 0. The formal dimension is just the dimension of G times B plus, which is negative. So it wants to be empty as far as the index theorem is saying, but it's not empty because there's the trivial flat connection in it. And that causes, in that case, that's a typical case where the Uhlenbeck compactification for non-zero energy guys isn't going to be everything, because there'll be you know, the higher energy moduli space. This is a zero energy moduli space. High energy moduli spaces may be non-empty, but the limits won't include every won't include all collections of points that, so, right. Imagine I looked at the trivial bundle plus K, right? Then I won't get necessarily every collection, every point in the symmetric K product won't appear as a limit in this case. There's an obstruction. This is going to be in some magical way going to give rise to a constraint. I mean, there's a beautiful and interesting story there somehow. The self-dual connections on the four manifold are constraining the points at which bubbles can occur. But anyway, that's a interesting story. So this M check XP need not be all ideal instantons. Okay. And okay, but so let's answer A. So if G is SU2 or SO3, maybe pi 1 of x, or let's say, and if it's SO3, H1 of x with Z2 coefficients, 0 for safety, then for a generic metric, sorry, and P1 of P is negative, then for a generic metric, MP XG is intersect B star is smooth and of the expected dimension. So that's Uhlenbeck's theorem. Another theorem of Uhlenbeck. So this theorem isn't true in general for higher rank Lie groups. If you want to get smoothness, if you want to get smoothness of irreducible connections, actually, I don't think we don't know that it's false, but we don't know that it's true either. But we can introduce further perturbations of the equations, which I won't go into, but that will make the irreducible solution smooth. Now, we need to understand we also so and more generally. Called Uhlenbeck perturbations, or there maybe some other schemes. So But anyway, you need to do more work, but you can still, in some sense, have a generic situation where the generic for some bare set of metrics and perturbations, the irreducible moduli space is smooth. But what about when is the moduli space contained in the when does it consist of only irreducible things so that we really know it was really, really smooth? Well, that's more, So we know sometimes, again, if G is SU2 or SO3, we discussed that already. In that case, well, sorry, let me just say, the general situation is that, right, that the game is that if I fix P, then there exists a reducible if there exists H contained in G a subgroup, V subgroup, and Q over X, a principal H bundle with an ASD connection, and the stabilizer of H should be non-trivial. So it's contained but not equal to the center of the group with an anti-self dual connection, so that the associated bundle is isomorphic to P. That's tautological, but a bit useless. We should think about what this, in real life, what does this mean? So, for example, if G is SU2, well, the only interesting, there's two possibilities. Either H is trivial, or the center, I should say, in which case the bundle's trivial. Well, let's assume pi1 is trivial for simplicity, or H could be U1. So that means, in particular, I have this complex line bundle, so that if I look at the associated C2 bundle to G, it's equal to L plus L inverse if G is SO3. Story's similar. I now have an oriented R2 bundle over X. That's what I mean by R2 plus. So really a complex line bundle such that the adjoint bundle, my P over X, the adjoint bundle of P is isomorphic as a real vector bundle to L plus trivial bundle. Now, we know in these cases when there's an anti-self dual connection. So if and only if for all omega self-dual self-dual harmonic forms, right? That's that C1 of L, or the Euler class of L, cup omega equals 0 for all these omegas. And in particular, if B plus equals 0, that's a vacuous condition, so there's always such a guy. If B plus is positive, then as long as we, we need to prove something, but for a generic metric, no such exists. But the interesting thing to note at this point is how the characteristic numbers or characteristic classes of P relate to L. So for SU2, well, yeah, I mean, so that, yeah. How do I say it? Let's see. In the SO3 case, P1 of add P is just the square of the Euler class of L. And for SU2, if it's SU2, then I can look at C2 of E, and that should be minus C1 squared of L. So, yeah, we should think of this in light of our classification. So, at the end of the last class, I sketched this argument that you can't realize E8 plus E8 as the or minus E8 plus minus E8. Depends on what you think E8 is. As the intersection form of a smooth four manifold. Using these ideas, and now we can say that a tiny bit more carefully. So, so let's suppose, well, sorry. We can now answer the question, just a topological question, how many distinct reductions are there, right? And so for an SO3 bundle, again, one trivial, the number of distinct isomorphism classes of reductions of P is the number of classes plus or minus h, such that h squared is P1 of P, and h is congruent to W2 of P mod 2. Right. And for SU2, it's similar. It's or maybe said better, it's this divided by plus or minus 1. That's a better way of saying it. Right? And the answer is similar here. It's the number of classes k, so that k squared is C2 of E, and, well, there's no constraint. W W2 constraint doesn't. There's no W class anymore because it's simply connected in this case. Mod plus or minus 1. So the thing to notice is that if you look at, say, minus E8 plus minus E8, and you pick a class, pick H, and this argument, just say, pick H so that, or let's take P1 to be minus 2. Right. Then I want to pick up, I'm going to pick a I didn't sleep enough and my brain is not moving very fast today. So I pick, I want my P, I'm going to fix W of P. This precludes that W of P is 0 in this case. But let's say W of P is, I take something of square. So the important thing is that minus 2 is the maximal, because it's negative maximal square of a class here, right? And I fix this guy to be some W. Which is equal to mod 2 reduction of something that has square minus 2. And now you ask yourself the question, what are all solutions to the equation? Let's look at x, so that x squared is minus 2, or x dot x is minus 2, and x is congruent to W mod 2. Right. So if I have another solution, x prime has to be x plus 2 L, right? And I know that minus 2 is equal to that, is equal to x dot x plus plus 4x dot L plus 4 L dot L. And that's also minus 2. So x dot L plus L dot L is, what am I doing? Yeah. Sorry, that's just 0, right? So that means L is perpendicular to x dot L. But now I look at x plus L, which is this guy, right? It's this guy. This thing squared is minus 2, but this is L squared plus x dot L squared. This is the maximum you can get. So one of these has to be 0, right? which is just saying that the only solutions to this are x and minus x. Right? So, so there's a unique solution that, unique solution of the sign to the, so that the set that's parameterizing the reductions in this case, it has one element. And that's the thing that gives you this argument. If I look at the dimension of this moduli space, right, it's minus 2 P1. P1 is minus 2, so it's 4 minus the dimension of the group. The moduli space is one-dimensional. And it has this one, it has a unique reduction. So there's one point in it, but and again, it's a reducible. So what's happening is that, and the same story that I was saying last time. The model around this reducible, so H naught of this complex of the deformation complex is R. That's the Lie algebra of U1. The stabilizer, H1, well, let's suppose we perturb so that the moduli space is smooth. Then H plus is going to be, H2 of the complex is going to be 0. It's one dimension, the dimension of the moduli space is 1. So this had better be two-dimensional. And it's a representation of the stabilizer. So that U1 is acting on C. So the moduli space near the reducible looks like C mod S1, R plus. And now you see that. So on the other hand, can you bubble? So what was C of SO3? 4, right? So if you bubble, remember the Pontryagin number will go up by 4. It will go from minus 2 to plus 2. That's an empty moduli space. So this is a so this MPXG is compact. So this is so what we proved something more general than what I said. It's not just this. The only thing this argument used was that you had an intersection form, negative definite intersection form that had a minimum or maximal vector of square minus 2. No such thing can be realized by a smooth 4 manifold. And this is we proved baby Donaldson diagonalization, which says that if Q of x is negative definite, then that implies that Q of x is it's a direct sum of just minus ones. So, that's the real theorem. But what this sketch is meant to prove is a much simpler version of it, which is already interesting. It's already, it's proving, like I said, for example, E8 plus E8 isn't realized. This is this argument, I should say. Of Donaldson diagonalization. This is arguments due to Fintushel and Stern. It appeared a few years after after Donaldson's argument. But the advantage is that it uses almost no technology. I mean, we didn't need, it's quite a bit more work to prove Donaldson's diagonalization theorem using instantons.
So we don't need any condition on pi 1.
No, we do, because it gets more, I mean, I always kept saying pi 1 is trivial. And so if pi 1 has no 2 torsion, you're still okay. If pi 1 has 2 torsion, SO3 bundles can have another kind of reduction because because the bundle could reduce to an O2 bundle. If it reduces to an O2 bundle, then its curvature could be its curvature is a 2 form that lives in a twisted real line bundle, and that guy could have, so it's more complicated. I mean, that, it's somehow, with Seiberg-Witten theory, you can prove the sharper version. There's no constraint, but it's interesting to see. Anyway, interesting to see the most elementary version of this work out. Now, sorry, yeah.
Sorry, I'm a little confused. How did you conclude that the moduli space is like S1?
So, yeah, so what is...
Is it just because they can...
Yeah, there's I mean, the moduli space, the moduli space is a smooth one manifold. It's smooth. It's sorry. Yeah.
Maybe I think I just don't understand what happens up there.
Yeah. Sorry. So let me explain that a little bit more quick. Yeah, that's right. This was the next board to use. Right?
That's just a formal consequence of that it has to be.
So what does the moduli space look near irreducible? So remember so we've got our slice theorem. So a neighborhood of that's A, the connection, in AP, if, let's say G is SO3, and H is U1, or SO2. That's really the situation that we're thinking about just at the moment, so the stabilizer of H is also SO2, right? Stabilizer under conjugation of an SO2 subgroup is in SO3 is itself. And so a neighborhood of A looks like the slice times the looks like the slice times the gauge group, but divided by the stabilizer. Now, we have in here, but in the neighborhood of the equivalence class, in the quotient space, looks like the slice divided by the stabilizer. So we need to understand what the stabilizer looks like as a representation of, the slice looks like as a representation of SO2, but our connection's reducible. So, we've got our deformation complex, which, so add P is L plus, is trivial real line bundle plus L. And what we've got, so there's the infinitesimal gauge transformations going to omega 1 of R plus L, going to omega 2 plus of R plus L. That's the plus A. Because this connection preserves the splitting, this splits into, and here we can do, I'm suppressing the manifold, but this splits into this, and omega 1 and omega 2 plus of L. Okay, the top row, you should be able to tell me what the cohomology is. What is the cohomology in the top row? So this is 0?
Oh, sigma 0.
What? Omega 0. Functions.
Is your space connected? R.
R. So, R. Yeah. Only Peter understands the joke. But anyway, that's R. That, Paul. Well, I wanted that one.
Oh, well, you pointed to that.
No, I think I pointed to that one. Genfeng.
0?
Good. That one.
H2 plus.
What's H2 plus?
R to the 0.
It's 0 because our manifold is negative definite, right? That was the assumption. So this is 0. Great. So this part has index minus 1. We have to have index plus 1. So, okay, and then we have to do a little bit of work, but it turns out 0, this guy is, is really R2. This guy's also 0. That's how you get your 1 total. But this is where the SO2 is acting. Right? So SO2 is acting on this R2 as rotations. So, I mean, now I can, if I say it that way, maybe it's even nicer. But the important point was that there was a unique reducible. So there's only one picture like this. The rest of the moduli space it's a smooth one manifold away from that point, and it's compact. All right. So what we've got, again, is a smooth, compact one manifold with one boundary point. There is no such thing. So that four manifold couldn't exist. Yeah, what else then? No, okay, yeah, so, and then the rest of the lecture was going to define the Donaldson invariants. I guess that's not going to happen today. Yeah, oh well. What else can I say in 2 minutes? Right. So maybe in 2 minutes, let me explain very vaguely Donaldson's proof of the diagonalization theorem. So Donaldson's proof it is much more kind of clever and difficult. So what Donaldson did was he took a SU2 bundle over X with C2 of P is 1. So then the dimension of this moduli space, expected dimension, is 8 times 1 minus 3, so 5. So it's a 5-dimensional moduli space. We have something that differs from the trivial guy by adding an instanton, so we can bubble. Right? So the Uhlenbeck, or the ideal instantons on this X look like this MP of X and G union MP minus 1, which is the trivial bundle of X and G times X. One deep result is that actually in this particular case, the Uhlenbeck, so this is the trivial connection. We're assuming that pi1 of X is trivial. So this consists of a point, which is just the trivial flat connection. And the Uhlenbeck compactification is actually exactly this. This is. So we're starting to see that X is the boundary of a 5-dimensional manifold. But it has some singularities, and the singularities count, from before, the number of reductions is equal to the number of solutions, k squared is minus 1. And so the picture around each of these is more, it's almost the same picture as this, except that instead of, this is still the same. It's still R plus, plus a complex line bundle, square of a complex line bundle, the adjoint bundle. But what happens is, so this part's the same. The dimension is 5, so this becomes a C3, a 6-dimensional thing with a circle action on it. So the picture is that this moduli space looks like it's got this 5-dimensional moduli space. Part of its boundary is X, and then these look like cones on CP2. And so the difficult things that you have to prove is that that actually X is precisely the boundary of M, and you need to prove that that M is orientable, and that with respect to that orientation, each of these CP2s are really CP2 and not minus CP2. So, but then what you see is if this is orientable, the manifold is cobordant to a union of CP2s. So its signature is the number of CP2s. Its signature is B minus. So the number of CP2s is this number. So that means that actually there are exactly enough solutions to that equation to diagonalize the form. Okay? Okay. And then in the last, now we have the Donaldson invariants too. No. Okay. I'd be happy to give a lecture next week, although I wasn't planning on it, if you would be happy to come to such a lecture next week. Some people are saying yes. Okay. So I'll try to make sure this room, or we'll post something about that. Then we'll actually define the Donaldson invariants. And then we'll do Floer homology after that. Okay.